All right, people, welcome back. I hope that those of you at home got the chance to try number 6 and 7 on your own. We got some volunteers, put them on the board here. And we will look over their answers now. So here we had a piecewise function. And at x equals 2, even this part of this formula is undefined at x equals 2. But we don't worry about that because it says we only use it when x is not 2. When x is 2, that's our y value of 10. So that's a 10 down there. And then these 11.47, 11.9 something, 12.0 something, 12.6 something. Don't mistake these as 7s. These are 1s. So this is what the graph looks like. Looks sort of like a parabola, which might not be a big surprise because you're dividing a cubic by a linear function. So you should get something of degree 2. And so here's that one lonely point at x equals 2, y equals 10. And we have a hole in the graph up here. And the conclusion by our brave volunteer was that the limit is 12. People agree that the limit is 12? Yes? Do we care what happens at x equals 2? We don't care, right? So this 10, we completely ignore it. So whenever you're looking at one of these tables and using it to try to help evaluate a limit, you can just put your hand over this, what happens at the actual value, because we don't care. This could have been a 10, it could have been a million, could have been a 12, could have been undefined. But these numbers, 11.9 whatever and 12.0, these are getting closer and closer to 12 from both sides. And that's why the limit correctly is 12. Good job. Anybody have any questions on that one? And then number 7, we didn't have a piecewise function. So this was interesting at x equals 0. And at x equals 0, the denominator is 0. So the volunteer correctly wrote that the function is undefined at x equals 0. But when x gets closer and closer to 0 from either side, and you want to make sure your calculator's in radians here, it looks like the y values are getting closer and closer to 4.5, which is why correctly the limit is 4.5. Limit as x goes to 0. Right? It's the same from both sides. Both y values are coming up closer and closer and closer to 4.5 as x gets closer and closer to 0. Good work. Question?
Shouldn't we fold 9 instead of fold 5 in the 0.01 and negative 0.01? Because it's kind of
This should be 4.4. 4.49 something. Did other people get that? 4.49 something? Yeah. 4.9 something? And this should also be a 9? Okay. That's all right. In any case, they are getting closer and closer to 4.5, so that is what the limit is. That's correct. Anybody have any questions on our first week in the seminar looking at limits just intuitively? We haven't proved anything because we don't even have the tool to prove anything yet. All we're doing is looking at the pattern of the numbers and looking at the graphs and making our best guess. For all we know, something crazy happens when x gets even closer and closer to 0 here, and the graph jumps up to 23 million. It doesn't. 4.5 is correct. But we haven't proved that yet. And we can't prove anything because we don't actually have a real definition of what a limit is, just as Newton and Leibniz and Euler and Bernoulli and all of those people back then, they didn't have a real definition either. So they also couldn't prove anything in the modern sense of the word. No modern mathematician would be satisfied with any of the things in terms of rigor with the things that they did. That's okay. They weren't so much worried about that back then. They were more interested in just solving the problems. And that is one way that some math classes are. You just solve the problems and you don't care about actually proving anything for real. But in the seminar, we want to go a step above and not just evaluate what the limits are, like we're going to do in the other main portion of the class. We want to be able to prove things, and for that we're going to need the real definition. So if you look at the bottom of the handout that you got today, the week 1, it tells you what we're going to do next week if you want to start looking ahead. The handout, for those of you who aren't here in class, is posted on the website. You can look at that. It tells you what you can read, just a few pages there, to get ready to start looking at the formal definition of the limit. That's going to be exciting. It took almost 200 years for the greatest mathematicians in the world to come up with this formal definition of the limit. We're going to get to see it next week. It's not easy. It's not a trivial definition. So you really are going to have to work at it to get a good understanding of it. And that's what we're going to spend the next 2 weeks doing. And we have a nice applet for you to use to explore this definition. We'll be using it next week. And yeah, so to understand any sort of complicated definition like this one, it's going to take some time and effort. And that's what we plan to do for the next 2 weeks. All right, we'll see you in a week.